In this video, we're going to explore the pH of a variety of mixtures of weak acid and their conjugate weak base. Now, we could calculate these all out full, plug them in, rearrange the equilibrium expression, but that's a lot of calculations. So how can we do this more simply? Well, conveniently, the Henderson-Hasselbalch equation lets us do that nice and quickly. If we want to know the pH of a weak acid-base mixture, what we need to know is the pKa of that weak acid, as well as the log of the ratio of the base over the acid. This equation allows us to much more quickly calculate out various mixtures of the same weak acid and weak base. So let's explore real fast. Let's start with ammonium. So our mixtures here on the right. Well, I have the Ka. To solve the pKa, I just need to take the negative log of 5.6 times 10 to the minus 10. We'll find that the pKa is 9.2518. 9.25. So for any of these mixtures, I can solve the pH by taking the pKa and adding the log of the concentration of the base divided by the concentration of the acid. 9.25 plus the log of 0.00003 divided by 0.23. So our ammonia is the base of the ammonia-ammonium conjugate acid-base pair. 9.25 plus the log of those, we find that the pH is equal to 8.61. Now, does that make sense for a minute? Well, one convenient thing about the pKa is that is the pH when we have equal amounts of weak acid and weak base. Remember that when your Ka is equal to your H plus, your base, over your acid, if you have equal concentrations of acid and base, they cancel out. Your H plus just becomes equal to Ka. Well, negative log of your H plus, negative log of your Ka. Your pKa is the pH when you have equal amounts. So we're a little bit more acidic, 8.6 instead of 9.25. Does that make sense? Well, I have substantially more acid than I have base molecules. So instead of having equal amounts, I vastly increased my acid over my base, so I should be a little bit more acidic, which is what we see from our value, 8.6 versus 9.2. Let's try that down for a second mixture. Let's invert this a bit. Slightly different values, but way more base than we have acid. 9.25 plus the log. In this case, it's 0.25 for the base and 0.0008 for the acid. And we find that the pH is equal to 11.74. Well, that's more than 9.25, but I don't have equal amounts of acid and base. I have substantially more of the conjugate base, so I should be more basic, and that's what we calculate out. If I want to do that for my acetic acid, well, the Ka of acetic acid is 1.8 times 10 to the minus 5, so the pKa, 4.745. 4.745 plus the log of the base, 0.002 over the acid, 0.15. Our pH, 2.87. A mixture of 1 molar pure vinegar would be 2.37. So we have a little bit of base. It should make it a little bit more basic. If we think about a 50-50 mixture, it should have been 4.7, and we have substantially more acid than we have base. So we should be more acidic, which 2.8 is more acidic than 4.7. So it seems to be following the right path. And the final mixture, 4.745 plus the log. This time, much more base, 0.2 divided by 0.005. Our pH of this mixture, 6.35. Well, if it was Even, it would be 4.7. We have substantially more base than acid, so we should be more basic, and that's what our value comes out to be. So when we have various mixtures of weak acid and weak base, we can calculate it out fully using an ice table. However, we can also use the Henderson-Hasselbalch equation to relate the pKa plus the log of the base over the acid to the pH. This can simplify our calculations quite a bit.